So yeah, I'd like to look at GDS today, just make some highlights, answer some questions, and then I guess summarize NOR is what I want to do. And then for this week, you're going to work on that and also on regression. As I mentioned, the tests you'll have 3 days to do the tests. I'll put it up on Saturday. You have Saturday to Sunday, Sunday to Monday, Monday to Tuesday. So you have some time. And so the units of the test will be these 4 units. Modules 2 till 5. And you have in the platform old exams to practice. I think I put them up. Let's see where they are. In module 5. So I have two midterm exams for review here in module 5. And they include all of them. Yes, up until module 5. Now, module 5 is very short. I could even do it in 2 hours. So I hope you're getting the hang of this. These meetings are just to touch base and highlight, and otherwise, give you a brief intro or a summary, depending on where we're at. But everything you need is already on the platform. Okay, so when you come to these meetings, it's to clarify. So use the schedule to guide you. I have to adapt my 45 hours course to 36 hours, and this is the best way I had to do that. So hopefully you get the hang of it. So yeah, the test will be online on the platform for 3 days until Tuesday afternoon. All right, so let's start with GDS and see if anyone has questions. Are you seeing all this stuff? These are hidden from you. So let me use your view. Okay, so there's a bunch of short videos going page by page for you, and there are the instructions overall. What I want to talk about is maybe what's not here, or emphasize the things that students have difficulty with from my experience, unless you have some questions for me. So last class, I believe I put up the notes and the video. These are the old ones. So maybe I didn't. Because I did put, I thought I did. All right, I guess I didn't. So can you see the notes right now? Yeah. Okay, so we talked about the stem and leaf plot of the spending data, and I made you a summary. I also informed you that you should follow through and read the sample problems documents, because that's where the sample exercises and data sets are. So I left off with talking about the back-to-back stem and leaf plot, and we made it together. And then in the video, I believe I describe how you analyze that, just like I did the stem and leaf. And the most important thing there is that you find that Bruce data is more consistent, represented by a symmetric distribution. And whereas Maris is right skewed with one oddball. 61.
Pero y cuando fue a Brewer me dijo que no tenía.
One oddball
Ahora no.
measure that was determined not to be an outlier, but it is set apart from the rest of the data. So we, I suggest that that needs to be investigated further and conclude that Babe Ruth is the better hitter. Then I talk about Newcomb's data and error, measurement error, and drop some data points after looking at the data set in terms of observations, timing of observations. And it's obvious that something happened early on. These are order of measurement. So this is time really. And early on, there were some errors, and probably owing to the way these measures are taken. And so I defend dropping those and computing a new histogram. I believe I discussed making a histogram. Let me check. We'll talk about that in a second. And then I have the summaries here, how you should summarize with the 5 features of the distribution and conclude regarding the question posed. So that's what I did there. So the main thing about Maris and Ruth that I wanted to emphasize is the discussion about how you analyze symmetric data. So because I did spend time with you on the skewed data, and then I get to, if you didn't have a chance, I'm going to emphasize, please watch all the videos, including this one on standard deviation. You might think you know what that is, but it's really important to understand because it's really just an average. And statistics is about averages and relative measures. And when you start seeing that pattern, it makes it a lot easier. And that's how I will communicate about statistics in the end as well. All right, so I should probably be doing this with the other notes. Okay, so did you try this exercise here? Given the 5 number summary, are there any outliers? Did you try that exercise? Okay.
I saw the video.
Yeah, did you understand? Did you follow? Did you try it? I mean, you can't be passive watching and not trying, because when you get to the test, you're going to have to do it on your own without videos. So, well, I mean, you can watch old videos, but they're going to be different questions. So you need to practice. You need to practice without the answers. So, so I solved that here. Actually, no, that's something else. So this is an outlier box plot. This is for Maris's data, but I want to show you with the data I just asked you to look at. What was it? Page. This is on page 17. Okay. So this is the box plot for this 5 number summary. And when you draw it, you see that there's a long tail in the whiskers here.
Sorry, Professor, what is the page number? Because I cannot see it.
17.
Is it?
17.
Okay, perfect. Thank you.
And you see that there's the long whiskers here. So we don't have to check on the right side for extreme values because it's not a long range. But we check on the left side. To check on the left side, you have to go from the box here back 1.5 and make a mark. So this is what I did. I went back 10 minus 1.5 of the IQR. The box was IQR. The box range is 5. That brings you here. So therefore, what's the conclusion? I mean, the answer is there, but how can you state the conclusion in words?
Well, it's showing the outliers based on the quartile and how the box plot is behaving.
But which one is, what is an outlier? Which number is an outlier?
Well, the answer is saying 1, but it's because the 1 is the one that is outside of the range for the IQRs, right?
Can there be more outliers?
Yes, there could.
We do not have all the data. All we have are the 5-number summary. So this is the minimum value. This is actually a value in the data set. So that's why I know 1 is an outlier, but there could be more. In fact, between 1 and 10, how many observations are between 1 and 10? How many observations are between 1 and 10?
Well, including the 1 and the 10 or 10?
Not 10.
Well,
25%.
Yeah, the answer is 25%. There's 25%. And now I don't have the size of the sample. I don't have N. But 25% is the answer. 25% are between 1 and 10. 25% are between 10 and 12. 25% between 12 and 15, and 25% between 15 and 16. So if it's 100, then there's 25. All I know is there's a 1. That's all I know. I don't know anything else. Okay. So this is how you do the box plot and identify outliers.
yeah, Professor, but not the whole 25% would be outliers. It would be the ones that are.
I did not say that all 25% would be outliers. I said between 1 and 10, 25% are outliers. 25% of all the data, which I don't know how many there are. That's all I said. I don't know how many, but the comment, the statement I'm making is that there's just as many from 1 to 10 as there's 10 to 12. They're just similar values between 10 and 12. There's a broader range between 1 and 10. The point is, the question was, are there any outliers? And your answer is at least 1.
Okay.
There could be more.
Right.
As much as 25% of all the data. That's the maximum. As little as 1.
As much as 25% could be outliers, you're saying?
Yeah. They could all be over here. You don't know. You don't have a clue. All you know is that this is the minimum and this is the 25th percentile, and the rest are spread here. They're not necessarily spread evenly. There's nothing on this graph that shows that they are spread out even.
But if you had more numbers, the quartile calculation and behaviors would change, right? The box plot will look different.
25% are here, so no. If you had more and it had the same pattern, it would look the same. If it had the same pattern.
Right, but if you didn't, that's what I'm saying. If maybe you had more numbers that were closer to 10.
If you had different numbers.
Right.
So my main point is there's only, the question was, are there any outliers? Your answer is at least 1. There could be more. The maximum is 25% of all the data is here, could be here.
Okay.
That's the most. But there's no reason, even though I have a long line and everything looks uniform, it's not necessarily the case. I don't know. I don't know. Okay, so Then I come to a question about symmetric distributions. How do you identify outliers for a symmetric distribution? Can I use the same rule, 1.5 times IQR? So when might you have outliers? When you have a very flat distribution, and you have a very flat distribution and things are very spread out, you could still have outliers, data points very far from the rest. And yes, Marla is right. You do not use the 1.5 times IQR rule. Patricia is right too. You use this range. You have to check outside of 3 standard deviations. So we use the metric, the measures we take for the symmetric distribution, the mean and standard deviation, and we use them to interpret if we have strange or irregular values. So I asked to check for the outliers in the pocket money data, remembering the mean and standard deviation. This is where I calculate the standard deviation. Within 3 standard deviations, you find these values here. And so the data started at 5, I think, and went to 16. So all of the values fall within 3 standard deviations. What does it mean? What is the conclusion? Marla is right. There are no outliers. Okay, so first of all, the shape, identify the shape, and then you can come to those kinds of conclusions or assessments and then conclusions. So there are no outliers in the pocket money data. And I'm making that point because I'm going to talk about normal distributions soon. And normal distributions are structured to have outliers, but it's not necessarily always the case with data. So then I talked about the hot dog data. Oh, and I want to talk about the outlier box plot. So here's an example of an outlier box plot. What you do with an outlier box plot is you go to the side, you go on the side where there's possible outliers, and you mark the threshold of 1.5 times IQR plus Q3 or minus from Q1. So you find the limit, and then every value beyond that you mark with, you identify with a dot. And that way, visually, I can see there are 3 outliers, 3 extreme values.
Can you write the equation you just mentioned? Right on top of it.
I am not going to write it again, but it's here. It's in this box.
Right.
That's on page 16. So if it's on the right, you add 1.5 of the range of the center. The center is like a regular pattern. It's showing you how spread out the middle 50% of the data are. And we use it as a baseline and allow a little bit extra, like 1.5 of it, to see if we can catch all of the data. If we don't, we say the data sitting away from it is a statistical outlier. You can do the same on the left if you see that you have extreme values on the left. Okay, is that enough time? Did you write it?
Yeah, so it would be Q3 plus the 1.5 times the IQR, or Q1 minus the 1.5
Exactly.
times the IQR, right?
Exactly. That's right. So this one was the right side that I showed you. The outlier box plot, and I'm emphasizing this because most students don't read this little section of the notes. It's a very specific box plot where we stop the whisker right where the threshold is. So this is Q3 33.80 plus 1.5 times the IQR of this. That will be there. And I mark the outlier. So we did this together. This is the spending data, right? We did this together. These were the 3 outliers we found. So yeah, I'm doing this to emphasize things that I do want to look at the histogram. So then there's just some problems here for practice. All right, weighted distributions. Let me go, not weighted distributions, but weighted mean. Let's look at this because some students skip over this to their great problems anyway. All right, so what is a weighted mean? So how many of you tried this exercise, example 1? Or yeah, how many tried? Let's put credit where credit is due. How many people tried that problem? No one? So this is why I do this, because sometimes students don't get around to solving this. Okay, so try it. Try it. So try not looking at the answers, just attempt the problem, and I'll do this one, and then we'll talk about the others. How's it going? Did you get an answer yet? Okay, so let me share this. All right, so if you, okay, some people did it, it's good. So if you assume this is a regular average, you would take assignments in midterm and final grades add them up and divide by how many there are. So 90%, 100%, 60%, and 50%. A 90, 100, 60, and 50. And you would add them up and divide by 4. So how can I do this on my calculator? So I told you to buy this calculator. So I have in the videos and the pre-recorded ones that are just edited. That one I'm using a different calculator, and then in the video in class I should be using this one, the BA2 Plus. So I'm going to show you a few things here. So let's say I want to enter this data as statistical data just to get an arithmetic mean, just a mean, an average. So there's data in there. I need to clear my calculator. How many of you got the calculator? I'm going to just show you how to set it up. I'm going to show you the setup. I highly recommend this calculator. You'll appreciate it when we get to, yeah, the app's great. Okay, good. It's like 20 bucks and it's always in your purse or at your side because it's in your phone. All right, so, all right, so you're with me. Let's turn the calculator into stat mode. So I do that by hitting second data. If there's something in there, I need to hit second and down here, clear work to clear it. You have to be inside the worksheet to be able to clear. So now I start entering my values. I can enter it as a decimal. I can enter it as a percent. So 0.9, enter, and I scroll down and it asks me for Y. Y can be used for frequency or Y can be used for another variable because this is a two-variable statistical, well, it's a two-variable calculator. It's a finance calculator, but and I use this course to teach finance as well. And you could use it in your finance class as well. So the Y can be frequency, like how many times I see 90, or it can be used as another variable, second variable. In this case, we don't use it. Its frequency is 1, so it's like a 1. So now we put in the next value. Oh, wait. I put it in percent, right? Let me check back. Yeah, so I put it in percent, gotta be consistent. So the next one has to be 1 or 100. And there's one of those, and I scroll down. Then I put in 0.6, enter, and I scroll down, and 0.5, enter, and I scroll down. And that's it. So that's my data. I can scroll through to see it to make sure I did things right. One of those, 100%, one of those, 60%, one of those, 50% of those. And now I ask for the statistics. So I hit second stat to see the linear, that's what LIN stands for, the linear estimates. And I guess we'll talk about that when we get there. So N is 4, and N for the sample size, 4 observations. The mean is 75%. And then there's some other statistics here. So let me talk about this. So this is the standard deviation of the sample. What does this measure? Right. So this one is a standard deviation of the sample. This is the mean of the sample. And this one, so we may have talked about this, right? This one is treating the calculation as though it is not a sample, but a population. And if it's a population, you divide by the sample size, and you treat the sample size as the population size. The sample standard deviation divides by a number that is smaller, one, you minus one from the denominator or from the sample size, because of some discussion I have in the videos about degrees of freedom. Because by using the sample mean in the calculation of the sample standard deviation, you lose 1 degree of freedom, so you have to divide by 1 less. This makes this number effectively larger than if you divided by the sample size. And in terms of how I use the standard deviation, I use it as a spread of data. This is more likely to spread out across the data, blanket it and cover more in each standard deviation from the mean. So that's the effect of it. The rationale is regarding degrees of freedom. And theoretically, you can show that if you don't do this, calculating the sample standard deviation this way, you will have a bias estimate of the true standard deviation, the population standard deviation. So I have this discussion in the notes and in the videos. The main thing for you at this moment in practice is just to know that you don't use this one. You use this one unless you have all of the data. Okay, then you can use this one as though it's the population of data that you have. All right, so that's the data. So I got the mean of 0.75. So what's wrong with this? What is wrong with doing it this way?
It's not using the weight of the
Well, because I have
assigned
extra
to the
information. I've been told that, whoa, each observation has different significance or value or weight. Okay, it has different impact or significance in my measure. So whereas this gives me 75%, it's actually what I'm doing is I'm pre-multiplying each value. I'm weighting them equally. You see that mathematically? It's like distributing a quarter weight to each one to get 75. But we're not going to do that. We're going to change the weights. And we're told it's 10%, 10%, 30%, and 50%. So we're going to change those because this is incorrect. Because these are incorrect, the weights are incorrect. And we're going to change the weights to 0.1 for 90%. Now I'm going to enter everything as decimals, but I just want to be clear about the weights versus the score. The score is happens to have a percentage units or measure, but I don't want to get you to get confused in which one is which. So this is 100%. This one is 30%. And I'm going to show you how to put this into your calculator. 60%. No. Yeah, 60%. This one is 50%. And when you do it that way, I'm going to show you how we'll do it in the calculator. So in the calculator, I mentioned the Y could be used as a frequency or a weight. So let's go back to the data, so second data, and scroll through, and I'm going to change the weights. I'm going to change Y to 0.1 for Y1. Y2, I'm going to change to 0.1. Enter. I'm going to change Y3 to 0.3. And I'm going to change Y4 to 0.5. And then I'm going to ask for the statistics, second stat. And what I'm going to do is I'm going to use the up arrow to scroll up, because it gives me the multiple x times y plus x times y plus x times y plus x times y. And it's denoted by, or in our case, it's going to be like the probability times like the value, right? So this becomes the weighted mean calculation. And I don't have to divide by anything because the weight is already a fraction. I just add them up. So this is the symbol for sum. And that's how I get 62. So you were mostly right. Does anybody want to see that again? So notice I start dropping the divide by, or sorry, I start dropping the indexing, like I equals 1 to n, because it's obvious there's only one variable and I'm scrolling through all the possibilities and summing them up after I multiply them. Oh, you want to see it again, Princessa, or you're saying that? Okay, you want to see it again?
Yeah, please.
Um, so second data, I enter the data with, well, I had all the values in 90, 100, 60, and 50, and now I'm just going to put the weights in as y. So I put in 0.9, and then the weight is 0.1, and I put in 100, and the weight is 0.1, and I put in 60, and the weight is 0.3, and I put in 50, and the weight is 0.5. And then I ask for second stat, and I use the arrow up to get this summation of the multiples. So this gives me the weighted mean. Now, there are a bunch of other statistics here that can be used, but I'm not going to use all of them. I'm going to use those for regression soon. This week, you're going to practice that for regression. Okay, and the next couple of examples that I have is just they're presenting the data so that you can compute the weights yourself. That's all that's really going on there. So I have here, so this was the formula I just showed you with the indexing I to n. I just dropped writing the I to n because it's obvious. And the weights must sum to 1 or you don't have a proper distribution of data. So then I have some information here. Let me copy this one. So this is, I do this three different times and apply basically the same principle, the weighted mean. So the weighted mean is a generalization of the regular mean. The weighted mean is a generalization of the regular mean. The regular mean assumes that all the weights are the same, like here. But if you have extra information, you shouldn't do that. You should try and get more specific, or accurate. And so for this one, it's the same sort of thing where you have a grade of 79 for women, and you have a grade of 67 for men. And you want an overall class score. Women did better, but you want an overall class score at any rate. There are more women in the class. Okay, so I do the same thing where I put my scores down. My scores are 79 and 67, but I need the weight. So how do I get the weight? "40 women out of 60 would be the weight for women,
20 out of 60 for me.
and 20 out of 60 would be the weight for men." Now, to get the precise answer, you do not want to just round these values, right? 4 out of 6 is a repeating decimal, I believe. So you want to keep that. So what you can do let's go back into the data. Let's clear the worksheet. And I'm going to put 79 in. And then I'm going to make a calculation of 40 divided by 60, or 4 divided by 6, and enter that as the weight. Scroll down and then put in the score, 67, enter down, and the y will be the weight. I'm going to do 20 divided by 60, and I'm going to enter that as well. And I'm done. Let's review. And then ask for the statistics and scroll up to get the weighted mean. And I got the answer. All right. And then there's a final one here that I did where I have the weighted mean, but the data again appears, it appears like the one I just did, but there's just so many different observations that it's more efficient to multiply by the frequency first and then divide by the total. So I do it at the end. So that's the frequency divided by the total, just like I did women and men. So depending on how I get the data, I'm going to manipulate it, but it's basically the weighted mean every time. Again, you can put this into your calculator. You can actually put it in as frequency, get the weighted mean, and then divide by 667. So try that. Try that on your own, because I'm going to just say something about the weighted standard deviation. So there's a weighted mean and there's a weighted standard deviation. The regular standard deviation is computed like this, as we discussed. But what if every observation has a frequency or a weight associated with of significance? If it's sample data, I will do this. Basically, it's the remembering what the variance is. The variance is the average of the square deviations from the mean, and the square root of that is the standard deviation. If you didn't watch the videos, the standard deviation, please go back and do that. What if the data don't come with weights, but they come with frequency. When I come to the point where I divide, I have to do the n-1. Unless I know the data is a population data, I have to do the n-1. That's the only catch there. Now there's, I have not sorted out if I can get the weighted standard deviation out of this calculator. So you got to do it practice the long way, and the long way can be done in Excel. If you're familiar with Excel, or just Endurance, doing it on pen and paper. This took me a while to even type up. I have a video, the video on YouTube with this has a lot of views on it. I think it hit Asia and it went sort of viral. So that was interesting. But you should practice doing the weighted standard deviation, and you'll see that my answers are similar with the weighted mean and standard deviation for the spending data, pocket money data, as they are when I assume they have all the same weight. The interpretation is the same, where I can say within one standard deviation of the mean are most of the observations, or I anticipate most of the observations in the future. Okay, so any questions about weighted mean and standard deviation? This is something you should just practice. And you'll see in the review exercises, I do have questions on the weighted mean, not so much on the weighted standard deviation, but you need to know this for when we get to module 7. I'm going to come back to this. Some other exercises for you to try that are old exam questions. And then I begin this discussion of scatter plots. So this is like an introduction to regression, where I took about 2 variables at a time. When you get to regression, you're going to learn how to actually estimate the measure R using your calculator. Okay, and if you've been scrolling through the options on that calculator, you'll see that for the data, it assumes that you're trying to correlate those variables, and it gives you the intercept, the slope, and a measure of R. So I'm going to show you how to do that with your calculator. Also, if you want, next week I can also show you on Excel. Okay, so those are the main things I wanted to say about GDS. Are there any questions that any of you have about GDS? How about the exercises, the quizzes, the practice?
I have one question, Professor. In one of the quizzes, they gave you the
Okay, so let's
weighted
spend an
mean.
hour on the normal distribution, and then I need to go early today. And hopefully you'll keep in touch with me about questions, all right? And I will post this video. I'll have to post last week as well, because somehow I thought I did it, but I guess I didn't. All right, so you do have a Connect exercise posted. I haven't heard anything about that. Oh, let's see. If I fix my microphone again. You should be able to speak. have my volume up. Very strange. Let me speaker, microphone. How's that? Can you speak now? Now? I'm gonna put my headphones in. Maybe that is better.
Can you hear us?
I can hear you.
Okay. Yeah, I think there was a question about Connect. So did you mention Connect about
I'm pretty sure I put it up. Let me see. Put it up last week. Pretty sure.
we cannot see your screen right now, but I don't think.
Well, I'm gonna check.
Yeah,
my-
thank you.
Assignment 2. It's there, but it looks like it didn't post. I don't know what happened. Okay, so it should be there now. It's due in like 3 days. If you can't do it in time, let me know, but try and get it done in time.
So when will it be done?
I said, May 16 at midnight. So that's Tuesday at midnight.
Tuesday.
And then this week I'm gonna
Mhm.
put up some normal distribution and some regression, and you can do them again due for Tuesday, next Tuesday.
Can you extend that to Wednesday?
Well, let's see if people need it. Will there be another one for next week? Yeah, there'll be before the test too. If you guys need it, just try and get it done because it's better to get it out of the way. If I extend it to Wednesday, then everyone. The whole thing is not to be working on Connect. Connect is just to finalize, that you understood things, but you really should be studying.
Okay,
Um,
thank you.
and I know because I was a student too, and I know sometimes the assignments get you all caught up and you think you're done, and you're not done just because you did the assignments. You need to get through the material. All right, so let's do normal distribution. Okay, so in the videos that I have on the platform, there's one video 9. I talk about relative frequency histograms. Have you had a chance to see that? Who has seen that video? So video 9 is here. Frequency and relative frequency histogram, and I draw the histogram for new comms data. And it's really important to go through that to see the depiction of the histogram. I want to get to the point. So I use the data. This is on my old iPad. It's kind of messy. And a very rough sketch, but I make this histogram manually. And I show you that whether I make the frequency histogram or the relative frequency histogram, they look roughly the same. I can make them look the same. It depends on how I put my scale. It's not a manipulation. It's just like the pattern is over what I really am interested in, right? But I changed the axis. What's the difference between a frequency histogram and a relative frequency histogram?
The percent, the relative frequency histogram compares with the total.
Yeah, the relative frequency is, can you see my cursor right now?
Yes.
Okay, the relative frequency exactly is going to graph as with the amplitude or the height of these bars, the percentage of observations, whereas the frequency histogram counts the number of observations. A few differences first between the two of these. This one just shows here, and I put in each of them if there's any debate about how high this is, right? It's just a sketch. It's how many observations or how frequently we see the different classes. So these are also divided into classes. Different from the stem and leaf plot, I allow for continuous values. I use a number line where I can use fractions can be implied between them because time and seconds can be counted with decimals, right? It can be a portion of a minute or these are nanoseconds, but okay. So so that's one thing. So this is it counted in numbers. Here I'm counting in percents. And the important thing is that every relative frequency histogram will sum to 100%. And this makes comparison of different sizes of distributions easier because they're all going to be 100% if I make a relative frequency histogram. The discussion I use is that the discussion I take, the argument I pursue is that the 5 features of the distribution, if you make a relative frequency or a frequency histogram, is the same. You have the same center, the same shape, the same spread, the same peaks, and the same outliers and gaps. You'll see the same thing. So the only difference between choosing one or the other is that here you have that 100% total, which makes it easier to compare distributions of unequal size. Also in reporting, it's a very quick thing to say, look, between 25 and 30 nanoseconds, almost 50% of the observations appear. It's a really easy number to communicate. People understand what that is. Even my niece, who's 8 years old, understands that that's a lot. So over here, when I say 28, nobody really gets what that is. And they'll have to ask you how many observations were there, okay? So that's kind of two things: advantage, easy to communicate, and the fact that it's always 100 from distribution to distribution, from data set to data set. All right, so the tendency is then in statistics to use the relative frequency histogram, although in reporting, people often report using the frequency histogram to show how their data spreads out, which has, a different purpose. Now, comparing the histogram to the stem and leaf plot, how would you compare the histogram to the stem and leaf plot? How are they different?
Stem and leaf is for a smaller sample.
Okay, 1 point, yeah. So stem and leaf is for a smaller sample, and you can use a lot of data and put it into a histogram. Very good. And I did mention that too. What's another reason? What's another difference between stem and leaf and a frequency or relative frequency histogram?
It gives you the exact values.
Right. So the stem and leaf gives you the exact values. Here you don't see the values. Okay, so in the relative frequency histogram, 44% are between 25 and 30. Are the numbers all going to be 25.5? I don't know. They could all be 25. They could all be 25. I don't know because I just said that they fell between 25 and 30, not including 30. I have this discussion when I make this graph, this chart. So you don't know the value. Stem and leaf, you can actually see the values, every value. Okay, so that is the pro and the con. Relative frequency and frequency histograms, you can put a lot of data in there, but you lose the detail. It's a trade-off. It's always a trade-off. Everything's a trade-off. Okay, so that's important to know. All right, so from the frequency histogram discussion, let's go to normal distribution. So we have 45 minutes, and I'm not going to go through the long introduction and discussion about normal distributions because many of you have had experience with the normal distribution. What I'm going to do is actually just apply it. So spend your time this weekend or this week looking at why we do things with the normal distribution. What the theory is behind the normal distribution. I'm just going to apply it right now. And then regression, we will discuss next week formally. I can spend the whole class on it or a portion of the class, or we can do some problems together in the first hour or so. So yeah, we'll have 3 hours together next week. So what I want to do right now is just talk about how we apply the normal distribution. And for me, it pretty much starts here. I'm going to show you my iPad again. So this is in the NOR notes or the module. Where are we? In the module 4 notes, slide or page 19. So you're going to work on that with all the instructions I give. And I'm going to start on slide 19. So this is the way that I cut through and give the point to people who are still learning and satisfy the people who have already done this or know this. So we're going to start here. Michael Jordan's height is 78 inches. Men have a mean, so I'm using the Greek letters here. When I use the Greek letters, I'm insinuating that I have information on the entire population. So a lot of data have been taken over a period of time, and it indicates that on average, men are 69 inches tall with a standard deviation of 2.8. And the fact that I use these Greek letters implies that I think that is representative of all men. Also, I'm assuming here by presenting the data like this, and the manipulation I'm going to make with the data is I'm assuming that height is normally distributed or at least symmetrically distributed. Okay, so Rebecca Lobo is another basketball player. So these are basketball players. Her height is 76 inches, where women on average have 63.6 mean inches is the mean, and the standard deviation is 2.5 inches. So which basketball player is taller? How will you make that assessment? We have to make an assumption, right? We're going to assume that they are those are symmetric distributions and comparable. And I'm going to even go a step further and assume normality to do what I do next. I don't exactly that's what I'm going to do. I'm going to assume this. It looks, it's symmetric distribution, normal heights and weights are usually in a large population normal. So how do I assess who's taller?
You could do a box plot to see how is the behavior of the heights and see where Michael Jordan sits versus where the lady sits, right?
Okay, so box plot is usually used for non-symmetric data, but you can use them to compare. So that's a good point. Box plots are used to compare distributions, but that's not a bad thing to do. So usually use box plots to just analyze distribution that is skewed. Here we're going to assume normal distributed height. So what does it mean to be normal? It means that the data or the distributions are symmetric unimodal. There's just like one peak. And they follow the 68, 95, 99.7% rule. And what is that rule? That is within one standard deviation of the mean.
Sí, buenos días, profesora. Disculpe que la moleste.
Within one standard
Teníamos
deviation
una
of
duda
the
en el
mean, you
grupo.
find
Tuve un problema ahí con la computadora del trabajo, se me bloqueó.
within one standard deviation of the mean, you find 68% of the observations. Within two standard deviations of the mean, you find, oh, you guys don't see my iPad, sorry. I have to put the iPad up. Okay, so we're assuming normally distributed heights. So the distribution of heights are symmetric, unimodal, in other words, one peak in the middle, and they follow the 68, 95, 99.7% rule. Within one standard deviation plus or minus of the mean, 68% of the observations appear. Within two standard deviations of the mean, 95% of the observations appear. And within three standard deviations of the mean, 99.7% of the observations appear. So, are there any outliers? No one knows? Well, the question was, Marla, are there any outliers? If we assume normal heights? No ideas, right? Okay, so we talked about a symmetric distribution. And what did we conclude about symmetric distributions and outliers? This is what we said just less than an hour ago, I think. In a symmetric distribution, values outside 3 standard deviations of the mean are statistical outliers. So in a normal distribution, I told you that it's approximately, it doesn't have to be exactly, but approximately 68% are within 1 standard deviation, 95% are within 2, and 99.7% within 3. So are there outliers? Well, how much is outside of 3? The answer, I want to cover this. In a symmetric, exactly, you guys got the hang of it. So in a symmetric distribution that I'm going to assume is normal, it allows 0.3% to be outliers. Now, because it's symmetric, there's a left and a right side. 0.15% are outliers that are on the right side or right tail, and 0.15% are on the left tail. So you have extreme values, extreme high and extreme low values, okay? The normal distribution allows for outliers. So I'm tying together what we just talked about in GDS to what we're doing here. It still applies because I told you normal distribution is symmetric, so this still is a rule, but it's 1 peak. And I had to say that because this could be symmetric, but that's not unimodal. This is bimodal. Okay. And I tell you that it follows this rule, and I've gone so far as use the symbols for mean as the population symbol for me, and the symbol for standard deviation as the population symbol for standard deviation, because they are, because that's this, I had a lot of data, so much data that, and so much accuracy that I think, and representation that I think this represents everybody, okay? All right, so having said that, given this information, what do I do? Who is the better, taller basketball player. I'm going to check. In terms of standard deviations, I'm going to verify how many standard deviations Michael Jordan is away from the mean of data, right? I'm going to try and find out if he's outside 3 and then compare him. You know, I want to see if he's an outlier, and then I'm also going to see if she's an outlier and who's more of an outlier. Let's see what that looks like. So for Michael Jordan, I'm going to calculate what's called a Z-score. So this is Michael Jordan. This is a Z-score. I'm going to standardize the value 78. I'm going to subtract the mean and divide by the standard deviations and convert this into a measure of the number of standard deviations from the mean that 78 is. So you take 78, you go to his mean of 69, and you divide by the standard deviation of 2.8 for men. And what do you get? What is the Z-score for Michael Jordan?
3.21.
3.21. So is Michael Jordan an outlier?
Yes, it's above the 3 standard deviations.
Yes, he's above 3 standard deviation and he is an outlier. Okay, now let's check Rebecca Lobo. So for her group, 63.6 is the mean and 2.5 is the standard deviation. So you get, so women are shorter, and she's almost as tall as Michael Jordan.
It's going to be further apart.
Right, she's going to be 4.96. She's a real out there outlier. So she is the taller, relatively speaking, of the two, even though her overall height is smaller, but she's a taller woman basketball player, a taller woman in general. Questions for me? That's the answer. Rebecca Lobo. So you could actually get this information. You can get this information in terms of Z-score or Z-score. You can also get this information in terms of percentiles. What's a percentile? What's a percentile? So if you take a standardized test, if you've ever taken the GMAT, right? Or the whatever standardized test you've ever taken, they tell you your percentile. Usually they give you your percentile score, or you can find it. Percentile tells you how many people, what's the percentage of people who did worse than you. I mean, I'm making it sound harsh, but people who have a score lower than you, right? So it's looking at the people below, to the left of you. So if I make a symmetric distribution shape and I put 68, 95, 99.7 on it, that's going to roughly tell me how things spread out. But to get more precise, I gave you tables. So the tables are tables of percentiles, and it tells you for this table here, it tells you if you're here, how many people are below you, if these are about people, right? If this is about heights. So if we interpret this as for Rebecca Lobo and for Michael Jordan, we can do that. But it's all in terms of z-scores. So I translate all my numbers into number of standard deviations from the mean, and then I can compute on this distribution. So this is laid out to give me the area to the left for a normal distribution where you have the 68, 95, 99%, 0.7% rule invoked. And that's what I work on through the notes and show you how the table ascribes to that. So if I was going to do that with this table, let's see, this is the negative table. So it gives me the values because this is standardized. 0 is always in the middle. Okay, and then there's so those are for negative values, and then there's for the positive values here. So let's look on the table for, what was Michael Jordan again? 3.21. Look for 3.21 on the positive table. What do you find? So this is on page 21 and 22. I have the tables. Oh no, 22 and 23. Sorry, I have to go back. 3.21, right. So what does this table tell me? This is the 3.2, and then I have a 1. So if I go back to the top, the first column is the second digit of decimals, right? The second decimal. So I want to be in this column. 3.21. So what does that mean? How do we interpret that number?
Let's see, he's in the 99.93 percentile.
Exactly. So the 99.93% of other men are shorter than him. So the way that I write that is I say going to the Z curve, the Z curve, less than 3.21, I get 0.9993, which is 99.93% of men are shorter than Michael Jordan. This is just a symbol. This means the probability or proportion or percentage. That are below 3.21, 99.93. And if I was to draw that, it would be like, and this was normal, and I go through this discussion, it would be way over, well, it's an outlier, right? So it has to be like way over here, away. Beyond 3 standard deviations. And I teach you how to draw these, this curve as well in the videos. So this is 3.21. And then the area to the left is 0.9993 because the whole thing is 100 and there's still a few observations above him. Okay, now I can also do this in Excel. It's not hard. You just there's 4 different formulas in Excel for the normal distribution. And I work this unit talking about 4 different kinds of problems. And I do that for a reason, because you can translate all of that. That with those 4, you can answer any type of problem, any type of normal distribution problem. So let's see Excel for a moment. Oh. I think I'm going to go on Excel on my, because this thing keeps popping up. I don't want that. Annoying. All right. So if I want to solve this problem in Excel, I use equals, norm, and you start writing norm, and you see there are several 1, 2, 3, 4, 5, 6, 7, 8 functions. So I'm going to just focus on, you're going to see there's just really 4. So there's norm.dist. And if I put an open bracket, it asks me for things. Oh, where to go? That's not good. No, I'm going to go on my computer because this is not the best way to demonstrate. Let me do it on my computer. All right, so let me share my Excel. So I say equals norm, and let's do exactly what we did. We're going to do what we did. We use the standardized distribution. We used norm.s.dist. Oops, dist distribution. And then it says here, you see it says put a z in, and that's it. And then it says put cumulative. Okay, so I'm going to put the z in was 3.21. And then I'm going to say, yes, I want the cumulative function. In other words, I want all the numbers to the left added up. So I hit 1 or true. And that gives me the same result. So you get from Excel much more detail than the table. The table only gives you up to 4 decimal places. But in fact, this is an infinite decimal answer, right? So if you use Excel, just be patient if your answers are a little different than what you see in the notes or in problem sets. But let me show you the function here so you can see that. You can try it yourselves. Did you try this before? And some people like it, and I like to make it available in this course that's distance. I mean, you can do whatever you want. Just don't ask anyone for help on the test, but you can use whatever resource you want. You can do it manually. You have to write out your answers manually for me. If you, yeah, Gloria, it's,
Sorry to go back. If you just use the norm dot distribution without the S, would it
So-
be different?
yeah, I'll do that in 1 minute, 1 minute. So if you want to use the table for your test, you can do that. Just you have to send me the table, and you have to send the table with the formula so I can see what formulas you put in there, okay? So let's do without the S. What do we get? So without the S is what, when you do the test, just going back a moment. So when you do the test, you're going to answer multiple choice questions, but you're going to send me your work, right? I want to see your evidence of your work with your handwriting. And if you use Excel, you can send me the Excel result with your all the code. So if I use norm without the S, it's going to ask me a bunch of things. You see, it's going to ask me X, mean, standard deviation. So here I go back to the original distribution. I don't have to standardize. I can just tell it from the get-go what I wanted to do. So X was the actual height of Michael Jordan. The standard deviation was 2.8. So mean, sorry, first mean is 69. And the standard deviation is 2.8. And then again, I tell cumulative. I want it to add up things. So I get the same answer. So that's how you can do that. Now this is handy. I mean, it's not that hard to do this. Some students have difficulty doing the reverse. So that's why this is handy to learn. So it's giving you the percentile. This is the percentile, or the left side of the table. Okay, we don't have too much time. Let's look at, well, I was going to get Rebecca Lobo. Let's just do Rebecca Lobo using this table then. So for Rebecca Lobo, this is for Michael Jordan. I want to do the same thing. I'm just going to copy what I did there and change the numbers. So I'm going to change, she just had 4.96. So let's do that, 4.96. Remember, you have to standardize to be able to use that. So obviously she is already the taller one for her group. So she's going to be further in the distribution, further in the tail. So yeah, there's more people to the left of her. She's at 4.96. So I'm going to go back to my iPad to show you the drawing of that. So in the discussion, the video, I just want you to go through to understand the mechanics of the normal distribution, but ultimately, this is the practical application of it. So for Rebecca Lobo, she also has a Z and she's at 4.96. And so that is going to be 0.999. It was like 9, right? 0.9999999. So actually, it pretty much rounds to 100%. Pretty much 100%. So she's way out there. The same distribution, but she's just out here. Like this is a very long flat distribution. She's way, way out here. And we're gonna say close to 100 or 100%. Depends how many decimal places you want to use, but to 4 decimals, she is 100%. Let's put the repeating decimals there. Make it a little clearer. Right, so she's way out there. All right, so let's look at the backward type problem before we go. Sorry, if you want to take a picture or comment. No, I mean, this is a master's course. It is academics. It's not just about being practical. I want you to understand the mechanics. I want you to understand the origins of all this. So please take your time and go back to understand all of this, because we're going to return to the normal distribution. This is actually the most important module, as we're going to use it till the end once we develop more of the theory supporting it, or to help us to get to the end. All right, so I do the same thing here with 2 candidates for admission to university. Eleanor wrote the SAT and Gerald wrote the ACT, and they're different scales of different tests with different scales. So how do you compare these 2? That's what you have to do here. So I'll leave these problems for you to try. And then what I want to do is talk about a backward type problem. So I'm going to skip to the bottom here. I'm going to take this information. And you can ask me if you don't feel confident, or you don't know if you got the right answer in doing this, you can ask me next class, or you can ask me in the forum. I think I'm going to make the forums mandatory next semester, because students write me in. It's often the same questions. I think the forum might work better, but I have to force the forum. Otherwise, people don't use it. Okay, I guess email seems easier because it's right at hand, but a student told me yesterday that he never reads his emails because he has too many emails. So why am I writing emails when students can't read them? I think the forum would be better. Okay. So this is the information, and the question is, what score would Gerald have to get to be in the 99th percentile? So I'm asking an inverse problem, a backward problem. I want to know the score given the percentage. Now, before, what I did here was I used the value, I got the z-score, and then I got the percentage. I'm going to do this in reverse. I'm going to give you the percentage, and you're going to give me the z-score, which will lead me to the value, the original value. So what score would Gerald have to be in the 99th percentile? Find the value of the grade that he would have to have, or the score. So now the symbol is this one. Did I write that down here? Yeah. Okay. So now the symbol I'm going to write is this, and I put X's in, okay, not Z's, because that's talking about the original data. But it turns out, in terms of spread, how spread out the data are, the X graph and the Z graph will have the same spread of observations. So I can use the Z in the place of X to accomplish this, to solve this. Just a moment here. I'm going to take this away down here. All right. So I'm going to draw this first, and I'm going to draw it like as though it's the Z that I did before. Okay, so this is my Z drawing, and I'm going to mark where 99% is. So let's just say it's like here. It doesn't have to be perfect. So first we're gonna find the z-score because that's properly going backwards, right? And remembering the steps. We got the z first, and then I got the percentage. But now I have the percentage, I need to get the z and then get back to the original values. So I'm gonna work backwards. I'm gonna start with getting the z using the percentage. So how am I gonna do this? If you go to the tables, it's kind of choppy in how you do that. Let's go to Excel and do this. You can do it in the tables too. Maybe I should do the table first. Okay, we're gonna go in the table and do things opposite. We're gonna look inside the table for this number. So we look inside the table for this number on the positive table because we're on the positive side. Remember, zeros in the middle here. So I look inside the table for 0.99. Remember, we found this number 0.9993. So 0.9900 is going to be so it's here between these two, which correspond to these z-scores over here. So between these two, I'm going to pick, the rule will be pick the one that's closest. So the closest one is this. So if they're different, pick the one that's closest. If they are the same, pick the average, or if they're the same distance apart, pick the average. So in this case, this one's closest. And so that corresponds to 2.33 standard deviations, 2.33 standard deviations. Let's confirm this result in Excel. I'm going to first write it down here. Let's confirm that in Excel. So we're looking at Gerald. And Gerald, we want to do the inverse function . Now there's two options. There's a normal dot inverse and the normal S dot inverse. Let's see the difference. So the normal inverse is what-
Professor, we don't see the screen.
Oh, okay, sorry. All right, so there are two options. There's the normal dot inverse and the normal dot S dot inverse. So let's just try the first one and see what it asks for. So if I use this one, it wants the original distribution data. So it wants to know the probability. It wants to know the mean and the standard deviation. And be warned, the Excel works like the table. It's only telling you or communicating everything to the left side, okay? Now we're okay because 0.99 is the left side. And when it says percentile, that is the left side. And then we're gonna put in the mean of Gerald, which is 18, and the standard deviation, which is 6. So we want to find, so this is going to get us the final answer, which we didn't even finish. But let's see. Oh, sorry. Do I have to put anything else? Nope, that's it. So it's going to give me 3196. This is the score that Gerald would have to get to be in the 99th percentile. So it gives you the final answer. If we use the other function, it asks for different information. Norm S inverse it's going to ask for the z-score. Sorry, it's going to give you the z-score, I believe. So you're going to say probability 0.99, and that's all you have to say. It's all you have to write. And here it gives us the z-score. So it doesn't give us the final answer, but it gives us the z-score, and you might want that sometimes. So this is the score on the test. And this is the z-score. So anything that says S goes back to the tables that you have. Okay, so this will give you the result in the table. So with more than 4 decimals, the answer is 2.326347. So what do I do? I'm just going to use the table result, but that's just for satisfaction that, you know, if you had more decimals on the table, it'd be a little more precise. Any questions about what I did so far? Like the final answer is this one here, but I want to show you the handwritten steps to get to the final answer, not just using Excel. I need to teach you both. Excel is good if I prefer you know what you're doing before you start using Excel. You're going to use it wrong eventually, especially when you do the right-hand side problems. You have to draw and sketch. You need to sketch these curves to maintain perspective on what you're doing and be aware of the limits of the table and the limits of Excel. Okay, I'm going to go back to my iPad. Okay, so I got this number 2.33. I saw it also in Excel, rounded to 2 decimal places would be 2.333. And this is like a 2-step process if you do this manually. First of all, you find the z-score. Secondly, transform z standard deviations from the mean is the same as z. What's the standard deviations for Gerald? 6 from the mean. What's the mean? 18. And this will give me my x, my original value of the grade that he needs to get. Z I found was 2.33, so I can put that in. And I will get the number I got in Excel. Let me put this here because this arrow is sort of standing up. So I convert this statement into a formula. And when you add it up, $2.33 times 6 plus 18 is 31.98. Which is higher, slightly higher than we got in Excel, but that's because of the rounding, right? It's going to be a slightly different. So when you work on my materials, you need to do things by hand to be able to get the same answers. Excel will give you slightly different answers because of the rounding issue. So are there any questions? So the final answer here is that Gerald would have to have 31.98 as a score to be in the 99th percentile. So just to recap the steps, we're going to do things backwards. Find the z-score. So given percentage, find the z-score, and then transform or what you're doing is what I call unstandardized. You're unstandardizing. So what we did was we found a z-score equal to the value of x, whatever variable we're using, minus the mean divided by the standard deviation. Well, now, rather than finding z, we're solving for x. We're doing things backwards. So mathematically, that is z sigma plus mu equals x, which is what we did. You could just as well plug everything into this standardized formula, but I give this a name and I call it the unstandardized formula to make a point that it's the same formula, but you're using it for a different variable. Now, we didn't have to standardize to solve for z here. We used to find z, we had to go backwards because we don't have an x. Basically, we don't have a grade to standardize. So we have to go backwards using the percentage. Usually we're finding the percent. No, we're going to go backwards using the percentage, get the z-score, and then transform by unstandardizing. So, all right, so I am going to stop there. Let me just show you, let me draw this for you to get you started, and then see if you can find the answer for Eleanor. Let me make this a little bigger, or let me move it away from everything I did there. So this is again a backward problem. I know it's an inverse or a backward problem because I was given a percentage. When I'm given a percentage, I know I have to work backwards. So in this case, let me get Eleanor's data. I'll get all the data here. Didn't work. So Eleanor's data. So again, we assume it's normal. It's not written there, but that's what you're basically assuming. And what score would you have to be in the top 5? Where on this graph is the top 5 percentile? Where would you want to be on a standardized score? You want to be in the top 5, the top 2.
95.
Well, where is it? Where do I put my?
On the right.
On the right side, right? That's clear. So it's going to be over here somewhere. And over here somewhere is where I want to find my z, with 5% on this side, or I write it with 4 decimal places so it looks like the chart that I'm going to use. It's 5% on that side, but every mark here has 2 perspectives, to the right and to the left. So what's on the left?
95%.
Right. So because of 95% and the table and Excel working only with the left side, I just use the 5% to determine what is on the left. So you can work on that manually and confirm with Excel. Okay, so work on that and then continue with your review of this course. If you need to meet with me sometime this week, contact me and we can arrange that. It might be Thursday or Friday. or if you just want to write me a quick email, you can do that as well. Okay, I'll post the this video, the other video from last week, which I thought I had posted. And if you need more time with the Connect, just let me know. Just let me know. I try and stay on schedule just because you need to spend more time studying for normal and the regression material this week. You do have 3 days to do the test. And by doing that, you know, if you haven't finished studying by Friday, as I've set the deadline, you can relax because you can, you know, you have days to be able to focus to finish your test and study what you need to study to complete the test. But do not wait until you have the test in your hands. Do not do that. There's too much material and you will get confused. In terms of the test being posted for 3 days, it will be, it'll be possible for you to enter and exit and enter and exit. So don't worry, you don't have to write it all in one sitting. There you go, Maite. Okay, yeah. So remember that the table is to the left, Excel is to the left. It's only about percentiles. You have to modify your approach to use those tools. And if you need more help after you review of the materials I've given you, contact me and we can look at your questions together. Next week, we'll meet for 3 hours and then I will post the test. Okay, questions? Have a good weekend. Have a good week.
So we're gonna meet next Saturday, 9 to 12, and then you'll post the test for what you said.
Yeah, I'll post the test at 1. And you
Okay.
get started and you have 3 days. Okay, bye.
Bye. Thank you very much.
Thank you. Module 5 is included on the test, Marcos. Yes. Module 5 is very short. It's very short. It's not a big module. Thank you for the question. Bye.